This is the screencast for section 4.3, example 9, analyzing a discontinuous derivative. Dun dun dun. So if function f is continuous in the interval, so that's huge right there. I'm going to underline that. F is actually continuous. So even though our derivative is discontinuous, f is going to be continuous. So when you draw your sketch of f, you know there aren't going to be any discontinuities in it. Okay, so f is continuous on the interval -4 to 4. The discontinuous function f prime with domain that is shown in the graph to the right. So I marked that as f prime, so I know I'm not looking at f or f double prime, that's f prime. Find the x-coordinates of all local extrema and points of inflection of f. Okay, so I'm going to have to test f prime for positive and negative values, which means I need to know all of the values where f prime changes sign. So that's going to happen, let's see, we start at -4, then from -4 to -3, f prime is positive. From -3 to -1, f prime is negative. From -1 to 0, f prime is positive. Then from 0 to 1, f prime is negative. 1 to 2, f prime is positive. And then finally from 2 to 4, that would be the end there, f prime is negative. So I can see several extrema. As a matter of fact, every single one of these values is going to be an extrema in f. Here we go. So first of all, f has a local min at x equals. Okay, local minimums are going to happen when f changes from decreasing to increasing. So f prime changes from negative to positive. So that's going to be -1, 1, and that's it. Alright, how about where f has a local max? That's going to happen where f changes from increasing to decreasing, so where f prime changes from positive to negative. So that's at x equals -3 from positive to negative, 0, positive to negative, and 2. Now we got to look at those endpoints. F prime is positive before a left endpoint, so that means f would be increasing before a left endpoint. So there is a local min at x equals -4, so I need to put that in there. The right endpoint, 4, x equals 4, f prime is negative, which means f would be decreasing before a right endpoint, ending in a local min again at 4. So I have 4 minimums and 3 maximums in f. Now I need to test for inflection points. Inflection points occur where f prime changes from increasing to decreasing or decreasing to increasing. So I need to look at where f double prime then would be positive and negative by relating it to where f prime is decreasing or increasing. So f prime starts out decreasing from -4 to -2, which means f double prime would be negative. F prime's derivative would be negative. Then between -2 and 0, f prime is increasing. So f double prime would be positive. The slopes would be positive, the slopes of f prime here. Then we're actually still increasing between -2 and 2 for f prime. So f double prime remains positive. Now between 2 and 4, f prime is constant. So f double prime isn't going to be positive or negative. F double prime is actually going to be 0. So f has points of inflection wherever f double prime changes signs. So that's going to happen at, let's see, -2, not 0, 2, and that's it. So those are our only points of inflection. Although, is that a point of inflection when it goes from positive to 0? By definition, it is not. 2 is not a point of inflection, only -2 is. So now I've got to sketch a possible graph of f. So my increasing and decreasing pass is going to result in something that looks like this, where f prime is positive, f will be increasing, and where f prime is negative, f will be decreasing. Now the f double prime pass, so the concavity pass, is going to look something like this, where f double prime is negative, f will be concave down, and where f double prime is positive, f will be concave up. So I have these two positives in a row that you can see between -2 and 0, and then again from 0 to 2. But now between 2 and 4, I need to look a little closer at that. F prime has a constant value of -2. So there isn't going to be any concavity, but the actual slope is going to be -2. So I'm going to put a little m equals -2, so I remember on my final graph that the slope of that little segment there is going to be -2. All right, so now let's sketch the final. All right, lots to think about here. Between -4 and -3, my graph is increasing concave down. Then between -3 and 2, decreasing, still concave down. Then between -2 and 1, decreasing concave up. Between -1 and 0, increasing concave up. But then between 0 and 1, decreasing concave up. So you can kind of see why f would not be differentiable right there. It's got that cusp. Then between, let's see, 1 and 2, increasing concave up. And then we have between 2 and 4, that situation where the slope is then -2. So I make sure it's got a -2 slope there, and maybe I put a little note to my grader, m equals -2, because I don't really have my y-axis marked there. And that does sum up what f would look like. It would not be, so there would be a break in differentiability here at 0, which you see, and not differentiable again at 2, which you can see. So f prime would look like this if this graph, f prime would look like this if f looked like this. The now try problem is number 49 and 53. 49 gives us the graph of f prime and asks us to analyze what's happening to f, and then 53 is going to ask us to sketch a graph of f. So here we go. 49a, find out where, so we're given the graph of f prime, which is already labeled there. Find out where f is increasing or decreasing. Now, I don't need to draw the number line to show where f is positive or where f prime is positive and negative. I can just simply put down f is increasing, and I know that's going to happen where f prime is positive or above the x-axis. So that's going to be from 1, definitely including 1, to, I'm from 0, that was the y value, from 0 to 1 with parentheses, and then from 3 to 4, also using parentheses. 4 is an open circle, so we don't want to include the value 4. And then I'm going to call that 5.5, so 5.5 to 6. 5.5 gets a parentheses, 6 gets a bracket. Part B, where is f decreasing? Well, f is going to be decreasing everywhere f prime is below the x-axis, or negative. So f is decreasing from 1 to 3. And again, from 4 to 5.5, not including 4 or 5.5, because again, that's that open circle. Let's see, C. Estimate the x-coordinates of all local extreme values. Okay, so extreme values are going to be where f changes from increasing to decreasing or decreasing to increasing. So that means f prime is going to change from positive to negative or negative to positive. So let's see, f is going to have local maxes where f prime, let's see, where f changes from increasing to decreasing, where f changes from increasing to decreasing, so f changes from positive to negative. So that's from 0 to 1, or excuse me, at 1. Not 3. Positive to negative does happen at 4. So there is a maximum of f at 4. And then that's it. Now what about f has a local min? Mins occur where f changes from decreasing to increasing, so that means f prime is going to change from negative to positive. That's going to happen at 3 and 5.5. Now I got to consider these endpoints. F prime is positive before a left or after a left endpoint, so f will be increasing, creating a minimum at 0, so I need to squeeze that in here. And then how about the right endpoint? F prime is positive before a right endpoint, so f would be increasing up to that right endpoint, meaning that would be a local max at x equals 6. And I just realized that I said the right terminology but did not write it in the right spot. So I did put my maxes here at 1, 4, and 6, and my mins at 0, 3, and 5.5. Okay, so now we need to sketch a graph. I'm going to do an increasing, decreasing pass. And then I have to do a concavity pass, which I haven't really analyzed, so I need to look where f prime is decreasing and increasing. Where f prime is decreasing, its derivative f double prime would be negative, meaning f would be concave down. So concave down from 0 to 2. F prime is increasing from 2 to 4, so that's concave up for f. Concave up again, increasing from 4 to 6, so it really just stays concave up forever. Now it does say in my instructions here that f is continuous, and I know I've got this little weird thing that's happening and a discontinuity in f prime, but I got to keep in mind that when I'm graphing f, my final graph of f should be continuous. So now looking at my concavity and increasing intervals and where the changes are, I get a sketch that looks about like that, but I have to keep in mind that I got an extra piece of information here in number 53. F of 0 equals 2. So I'm going to label this point as 0, 2 to show that I picked up that piece of information and did demonstrate that on my graph, and I'm going to label that as F.